Perhaps one of the great achievements of the last few years has been to build and operate telescopes that now allow us to see solar systems information. We already looked at this image in section 7 when we discussed resolution. This has been done through interferometry with ALMA, a range of something like 60 big antennas operating in the submillimeter. Of course, we always knew that planets should exist around other stars because our planet does, and we have our own solar system, so why should other stars be different? But one of the big questions has been whether we can actually find other planets. And if we find them, will they look anything like the ones in the solar system? Will they be very different? And also, would they form in exactly the same conditions and essentially reveal the same trends that we discussed in section 10? Trying to find planets around other stars has been like a major key goal in astronomy for many years. However, even though in artistic impressions we can always see the planets, the reality is that on average they're something like 100 million times fainter than the stars, because essentially all they do is reflect a little bit of the light, and therefore in real life we wouldn't really be able to see this planet. We would be mostly seeing a transit, for example, as we shall see. This means that direct detection of planets is incredibly hard, although it is now possible. We'll see which cases actually allow for that. On top of that, we'll see that there are essentially 5 main different ways to detect planets. Through direct detection, that is the most obvious thing, but is really challenging. We'll see how in principle we can detect planets through some positional wobble. We'll see exactly what that means. Through gravitational lensing, which is actually a neat technique, but it's not so easy to reproduce because it only happens essentially once. And finally, these two methods, which are currently the most prolific, most powerful methods. One is to use Doppler Effect, essentially radial velocity, and actually measure the movement of the star that is driven by planets orbiting it. And also photometrically, essentially via transit, so whenever a planet passes in front of a distant star and causes a dip. We'll see exactly how we can use these methods, what are the advantages and disadvantages. Direct imaging is extremely challenging for a lot of reasons. Typically, planets will be very close to their stars. That's by definition. I mean, they establish a bound system. Therefore, there are multiple challenges. On one hand, the star is way brighter than the planets, and especially in the optical, as you can see here, we're talking of something like 1,000,000 to 1,000,000,000 times brighter. It's really hard to find planets and to have the contrast to distinguish something that's 1,000,000,000 times fainter than the primary object. However, we can try to be smart and move into the infrared, where planets are not as faint as the stars, but we're still talking of a factor up to 1,000,000 times fainter. So this is still challenging. However, it can work, especially if we're looking at very large separations. So if we're looking at orbits that take a long time, where planets are really far away from their stars, this becomes doable, especially if the planet itself is very big and the star is not as massive. Therefore, this works the best for very cool stars and very large planets, almost as if they are binary systems. And on top of that, another neat technique that has been developed is a way to actually block the light of the star. And again, if you have a planet that's sufficiently far away, and if you block the light of the star, it helps contrast and you can actually find them. Therefore, direct imaging is extremely valuable, particularly to find planets with really long periods. They're orbiting very far away from their stars, but we're limited to sort of the big ones, at least for now. Another method that was actually proposed for a long time that really didn't succeed, but in principle is doable, is the astrometric detections. Essentially detecting a wobble as the star moves a little bit every year with something that we already talked about, which is called proper motion. This is doable specifically for a binary of stars where they have a very similar mass, but for planets it becomes way more challenging. The way this method works is essentially to understand that every year the star will never go to the exact same position. It has a proper motion of a few arc seconds per year sometimes, just due to the fact that we're orbiting the galaxy and so are the other stars. And if a star has no companion and no planets, in principle, as that happens, it will just move in a perfect straight line. However, if the star is a companion, such as a planet, it needs to be quite massive for us to see it, but ignore that. What will happen is on top of the star actually moving this way, it will actually wobble. Its position will actually be periodically varying up and down. And if we detect this, we can actually use the information to calculate or say something about the orbit of the other body that perhaps we cannot see directly. The reason why this method is not so promising and has not really led to a lot of progress is just to do with the accuracy that you need versus the actual change of position of a star on the sky as it moves due to its proper motion. Obviously, the greater the mass of the unseen companion or the planet, or the closer separation, then the greater the wobble. This makes it easy to understand that detecting binary stars in this way, even though it's tedious, it's definitely doable. But detecting planets in this way is almost impossible. You need to be really lucky and to be looking at a really massive planets very close to the star. Let's try to do that, and specifically thinking about the average separation between, say, a star and a planet. And the star will be denoted as 1, the planet is 2. In the lecture notes, that's even more explicit as star and planet. And we've seen that considering the center of mass and the way that the objects will orbit around the center of mass, we can actually write that the separation from the star to the center of mass, where you might see some oscillation, will be given by the average separation times the mass of the planet divided by the mass of the star plus the mass of the planet. Now, if we calculate this for Jupiter and the Sun, we can actually find it in terms of meters, or perhaps more valuable is to try to calculate it in terms of AU and to realize that this is a really, really small value. Now, imagine that we are observing the Sun essentially 10 parsec away. That would be a relatively nearby system. If we want to observe its wobble, we would actually have to be sensitive to something like 0.0005 arcsecond in something like 30 years. And these 30 years would actually come from the fact that we would like to detect the combined effect of Saturn and Jupiter. And Jupiter will have a period that's more like 15, 16 years, but Saturn is more around 30 years. And we also would like to repeat the measurements. Therefore, all things considered, this method is definitely not very promising, and it can get even worse, especially because if you look at planetary systems that are even further away than 10 parsec, which most are, then you would actually need to have an even better sensitivity. And remember that from the ground, the atmosphere blurs things down to about 1 arcsecond. And even with the best instrumentation in space, achieving this precision is definitely not easy. Another technique to detect extrasolar planets is the gravitational lensing technique. Now, this technique works when you have, say, a star and a planet that is essentially moving, and it actually moves in front of some distance source star that you're monitoring it. When this happens, actually, you can see the source star actually moving away or being gravitationally lensed. And what happens is you can look at how the magnification changes as a function of time, essentially as the system passes in front of your background star. And depending on the number of planets, you'll be able to detect multiple peaks. In this case, you'd be detecting the planet and the star itself. But if, say, the planetary system contains multiple planets, in principle, if you have enough precision, you'd be able to see the multiple peaks. Until then, you actually see, say, just a star, and then it goes away. In principle, this gravitational lens technique can detect planets of any mass, and therefore it is great. It's definitely not very biased. However, once this event, an event like this, is over, it is really hard to gather more information on the planet. Since essentially we're only seeing the background source, we can track the star, but many times it will be very hard to use other methods to confirm these planets. And therefore, it is really hard to learn anything more about the system.